Okay, we are live and continue the seminars of the National Observatory. Today I have the pleasure to introduce Professor Claudia Scóccola. She's a professor in the University of La Plata in Argentina, and she will talk a little bit about CMB. So please, Professor Claudia, you can start your seminar.
Thank you, Rodrigo. Thank you for the invitation to give this talk. I'm very happy to be here virtually this time, but I'm very happy to be with you today. So in this talk, I will present a new instrument called QUBIC that aims to measure the CMB polarization to detect or to put constraints on the B-mode polarization that will give information about the early epoch of the universe called inflation, in which the universe expands exponentially. So as I am a professor at University of La Plata, as Rodrigo said, and a researcher at CONICET in Argentina. This instrument QUBIC will be put in the Salta province in Argentina, in the region called Puna, which is a very good place to put instruments of this nature. So this is the outline of the talk. I will start reviewing what are the primordial B-modes polarization and why they are so difficult to measure. Then I will talk about the QUBIC instrument, about the observational site in Alto Chorrillos, and then I will talk about the capabilities of QUBIC to do spectroimaging. And then I will end the talk reviewing the current status of the instrument. So to begin with, this is a picture of the evolution of our universe, which is expanding and cooling down, right? And then our universe has an age of 13.8 billion years. And in the very beginning of the universe, when the universe was only 10 to the minus 32 seconds, it went through a exponentially rapid expansion called inflation, in which the scales grew very much and the quantum fluctuations turned into macroscopic fluctuations, which gives rise to the cosmic structure we see today. Then the universe starts continue expanding and cooling down. And when the universe was 380,000 years old, the temperature has dropped enough so the neutral hydrogen was formed. The photons of the primordial plasma decouples from matter and start traveling all the way through the universe up to today, in what we see today as the cosmic microwave background. Yes. So the temperature fluctuation of the CMB, the cosmic microwave background, is the radiation from the Big Bang, and it constitutes one of the most important observational tools to study our universe, both the early times and the late times. Because in the statistics of the anisotropies in temperature and polarization, we can see both what happened at early times and the imprints of the late time physics on the CMB. Why is that? Well, because we see the CMB as a picture, and the matter that is between the CMB and us can distort the fluctuations in several ways. For example, if there are clusters of galaxies in the line of sight, we will see the Zuniaev-Seldovich effect, that is inverse quantum scattering of the photon of the electrons, and we will see a distortion in the energy spectral distribution of the CMB. Another late time physics that we can observe on the CMB is the weak lensing that is produced by the matter and it distorts both the shapes of the temperature fluctuation and also the polarization pattern. And that would be effects produced after the release of the CMB. But of course, we can also test the physics of the recombination time, the time when the neutral hydrogen was formed, but also in the polarization of the CMB, we can see in the pattern of the polarization, we can see a footprint of what happened at the very beginning of the universe, at the inflation epoch. So why inflation is important and why it is needed? The standard cosmological model includes the inflation paradigm, that it was introduced to the model to solve serious problems of the classical Big Bang model. One of those problems was the planarity of the universe, why the geometry of the universe is so flat. The other problem that inflation solves is the large-scale homogeneity of the universe, why the universe is so homogeneous even on regions that are casually disconnected, that are outside the horizon, the causal horizon, yeah? And this period of exponential expansion at the very early, at the very early universe explains why these now disconnected areas were at some point within the same horizon, and so in thermal contact, yeah? But most importantly, the inflationary paradigm provides a way to produce the initial conditions of the universe, the seeds from where the cosmic structure will grow. Yeah? So it's a way of explaining the origin of cosmic structures through these primordial fluctuations. So if inflation produces these seeds, okay? But the inflationary period occurred at the very beginning of the universe, as I said. And this period, of course, is unreachable to observations. These fluctuations that are produced during inflations, the relevant ones can be described as scalar or tensor. Yes, our scalar mode or tensor mode. The scalar modes of the metric fluctuations are the source of the matter density fluctuations, which of course is leads to the origin of the cosmic structure, and also the scalar fluctuation produced most of the CMB temperature and polarization fluctuations, anisotropies. On the other hand, the tensor fluctuations, which are also known as primordial gravitational waves, leave a unique feature on the polarization pattern of the CMB. This feature we call B-mode polarization. So a detection of the primordial B-modes will constitute an indirect measurement of the inflationary epoch, yes? Okay, now, it is a unique prediction of inflation that it produces these tensor fluctuations. And the amplitude of the gravitational wave of the tensor fluctuations is related to the energy scale of the inflaton potential. Yes? So, for example, in the simple model of a single field inflation, this would be the amplitude of the tensor fluctuation, and it would be the potential of the inflaton field. And this would be the relation between them. So knowing or measuring the gravitational waves, the amplitude of the gravitational waves, we can know the energy scale at which inflation occurs. An important parameter that we introduce and measure in this kind of studies is the tensor to scalar ratio. This parameter quantifies the amount of tensor fluctuation with respect to the amount of scalar fluctuation. Yes, it can be described as the ratio between the amplitudes of the power spectrum of tensor fluctuation over scalar fluctuation. Then a measurement of R is a direct evidence of the presence of primordial gravitational waves or tensor fluctuations. Yes? And as I said, it will determine directly the energy scale at which inflation occurs. So this is what we are after, the tensor to scalar ratio, which is our figure of merit, let's say, our diagnosis. So how it is, I want to explain now how it is that tensor perturbation generated during inflation leave an imprint in the polarization of the CMB. How it happens that the polarization of the CMB tell us about the tensor fluctuations that are produced during inflation. Okay, let's recap a little bit and remember that CMB is polarized. Yes, I will explain why this happens now in the following slide. Now, most of the polarization, as I said before, is produced by scalar perturbation. And a little fraction is produced by tensor perturbation. Now, in this map, which is from Planck, in color we see the temperature fluctuation, and with the rods we see the polarization, both the orientation of the polarization plane and the amplitude. Now, let's go to the point. Why there is the production of polarization? A local anisotropy in the radiation field will produce polarization. Yes, in particular, a quadrupolar anisotropy at the last scattering surface, remember from where the CMB come, it will produce a certain degree of linear polarization due to Thomson scattering, which depends on polarization. So this is a picture, a very easy gift image that shows why we can produce from Thomson scattering polarized light from unpolarized light. Yeah, this is the process of scattering. But if we have isotropy in the energy, in the photon distribution, in the temperature, I mean, of the photon distribution, we will see no net polarization between, because it's very easily seen in the image. But if we have a quadrupolar anisotropy, in the sense that we have hotter photons on one direction and colder ones in the perpendicular direction, we will have, as a result, a linear polarization, a certain degree of linear polarization in the scattered radiation. So the scattering that is produced by, between photons and electrons at the last scattering surface is producing the linear polarization that we see on the CMB, photons. Yeah? Okay, but then this quadrupolar anisotropy can be generated or produced both by scalar fluctuation or tensor fluctuation. And these two different modes of quadrupolar distributions, on top you see the scalar quadrupolar distribution, and on the bottom you see the tensor, the quadrupolar anisotropy produced by tensor fluctuation, and this is different, and the polarization will be different. In particular, the density waves or scalar fluctuation will generate only what we call E-mode polarization. The polarization pattern will be curve-free. Yes, we'll have this shape schematically, of course. While the quadrupolar anisotropy generated by tensor fluctuations generates a polarization pattern which has this shape, which is diversion free, and is called B-mode. Yes, B-mode polarization. So what is to take the message to take from this slide is that scalar fluctuations cannot generate B-mode polarization. Okay, only the tensor fluctuation can. Okay, now let us remember how we describe polarization. Polarization is usually described via the Stokes parameters, but it also can be described via through these E and B modes, right? Okay, so the Stokes parameters are those that describe the linear polarization and are fields on the sphere that can be decomposed on expanded, let's say, on the basis of spherical harmonics with spin 2. So that would be the expansion, and this ALM will be the coefficient on this base. Now, if we combine these coefficients in some way, we can compute the coefficients in another base, yes? These are the E and B modes, and these are the coefficient of expansion in spherical harmonics, which means 0, the normal spherical harmonics. So these are scalar and pseudo-scalar quantities, but they are also local and, sorry, they are non-local because they combine information of different points around the points of study, because they describe a pattern. They describe a polarization pattern, not the polarization on one given point, but the polarization pattern. I say E is scalar and B is pseudo-scalar because under parity, E doesn't change sign, but B does change sign, yes? Okay, so E and B modes are is a way of describing the polarization that describe the pattern of polarization. And here I show you the E mode, and I want to say that E modes was already measured because they are produced by scalar fluctuation, and I will say more in a minute. And B modes are still to be measured. They haven't been measured yet. There are some bounds, some constraints, but we haven't been able to measure the B modes yet. So this would be the power spectrum, which is the way we describe the CMB, yes, and the temperature and the E mode polarization and the expected levels of B mode polarization depending on the energy at which inflation occurs, yes? And we haven't measured this primordial B mode power spectrum yet, okay? So let me state some remarks and some caveats, see? Yes, the detection of the B modes peaking at around 1 degree will be the footprint of primordial gravitational wave. If we are able to detect the B mode polarization with peaking around this angular scale of 1 degree, we will be pretty sure that we have measured the B modes. Now, B modes are also expected due to lensing of E modes, but occurring at a smaller angular scale. And this is, and remember when I talked about lensing, I said that lensing produces a distortion of the polarization field. So if I have a polarization field, which is only E mode, but then it goes through matter, and this matter, through the lensing effect, distort the polarization pattern, I may be able to measure a B mode pattern, but not primordial, right? Just produced by lensing. So this lensing has already been measured, this lensed B modes has already been measured, but they occur at a smaller angular scale. And since they are coming from E mode, they have larger amplitude, and we have been already been able to measure them. Another caveat, B-mode can also be generated by Faraday rotation of E-mode, again, a distortion of the polarization field, of the polarization pattern, due to the Faraday rotation effect, which can appear if there are magnetic fields present. But this effect depends on frequency, so we could be able to distinguish it. And lastly, density fluctuations can also generate B-mode by nonlinear effect. And this would produce secondary vector and tensor modes and B-mode polarization, but this this polarization would have a lower amplitude, and it would be lower than the primordial one that we are trying to measure. But we have to take this into account because at some point it may be important to consider all this and separate between the primordial signal and non-primordial signal. So, final remarks. Primordial B-modes have not been measured yet, and an important thing to say is that only 10% of the CMB is linearly polarized, and from that polarized light, only 10% or less is produced by tensor perturbations. So the expected B-mode signal is very weak. It's expected to be of the order of tens of nanokelvin, of a nanokelvin signal, right? So it's very weak, much weaker than the temperature and than the E-mode polarization. Moreover, the signal is contaminated by the emission of our galaxy. And our galaxy emits polarized light. At low frequency, it emits synchrotron emission, and at higher frequency, it emits the dust. Thermal dust emits polarized light, and we can measure, and it will be a contaminant for CMB. So it's important to, and these contaminants, the spectra depends on frequency. So it is important to try to measure the CMB at different frequencies to be able to then do a component separation and get only the CMB signal. Then, I think you agree with me that to be able to detect the primordial B-modes, we will need an instrument with very high sensitivity because the signal is very weak, and also good controller systematics to allow to know your instrument and be able to detect the B-mode and be sure that it's a primordial B-mode, plus the capability to measure at different frequencies to be able, as I said, to separate the cosmological signal from the foregrounds. So let me now introduce QUBIC again. So QUBIC is the Q U Bolometric Interferometer for Cosmology. It's an instrument, it's a telescope that will be observe the sky in the microwave part of the spectrum, and is focused on measuring the polarization B-mode. This is a picture of QUBIC at the lab in Salta, and this is a cartoon of the instrument in the shelter as it will be on the observational site. So QUBIC is an international collaboration of more than 130 researchers in 23 institutions in 6 countries, including Argentina, France, Italy, Ireland, UK, US, and Argentina. And these are some of the institutions the people are there. And the site will be in Salta province, that is in the north of Argentina, in the Puna Altiplano, And the place is called Alto Chorrillos, and it's a very high altitude is 4,900 meters above sea level. It is a site near the Llama site, which is an antenna, radio antenna from Argentina and Brazil. So they share some of the infrastructure. The QUBIC site is around 20 kilometers from San Antonio de los Cobres, where the lab operational site will be. These are pictures from the site. The works on the site to install the shelter are already quite advanced. So now let me talk about the infrastructure of QUBIC, how QUBIC works. QUBIC is an instrument that has a novel concept that has not been used in other CMB experiments yet. Normally, in general, CMB experiments are either interferometers or bolometers, but QUBIC combines both concepts into this design. Yes, so on the one hand, it has the sensitivity of bolometers, and on the other hand, it has the explicit systematic control of interferometers. So here you have a picture of the side of the instrument, but let me explain how it works with this picture. So once this is the window, once the signal of the skies enter the instrument through the window and some filters, we have a halfway plate and a polarized grid that modulates and selects the polarization. Then the radiation polarized with a modulated polarization, because thanks to this rotating halfway plate, goes through an array of horns that produces the interference pattern, which is the synthetic beams. Then this beam is collimated through some mirrors. These are already at 1K. And it goes through a dichroic that separates the signal into two focal planes that are at two different bands, frequency bands. One is at 150 gigahertz and the other is at 220 gigahertz. And these focal planes are covered by very sensitive detectors that are called TES, that are transition edge sensors that operate at 320 millikelvin. So here you have the interferometric pattern, and here you have the bolometers. On the right, you can see two pictures. These are 1/4 of the focal plane and the detection chain. Yes, and on the second picture, no, the B one, is the horn array. Yes, and it's composed of all these horns that are made in a single array. Very interesting there. And these are back-to-back horns, and in the middle you have the switches that allows you to open and close the horns as needed. Now, as I said, the transition edge sensor, the bolometers are very sensitive detectors. And this sensitivity comes from the fact that this material is cooled down to 320 millikelvin, because at this temperature, the material behaves as a superconductor. So the detector is set to this temperature, which in fact is the transition between normal and superconductive behavior. So if the sensor is set at that configuration, when it receives a very little amount of energy, the resistance will increase a lot, as you see in this plot, and this will allow to be detected. Let's say with a small amount of energy, you can detect a large change in the resistance of the material. This is how these sensors are so sensitive. On the other hand, as I said, QUBIC is an interferometer, so it can do what we call self-calibration. Self-calibration is a way of knowing your instrument better. And how it works? Well, if you have here a picture of the horn array plane, or these circles are each of the horns, and you open two of them, the result of the interference pattern will be fringes like this. If you open two others different horns with the same separation and orientation, you will have the same baseline. So the interference should be the same. But since the horns are different and the instrument is not perfect, ideal, let's say, the interference pattern will be different. So since in the ideal case, this should be the same, you can know, you have a way to correct your instrument, to know the instrumental errors, let's say. This is what we call the systematic errors. So in this way, we correct our systematic errors. And this is called self-calibration, and is possible only through the interferometer. Because it's only possible because QUBIC is an interferometer. Okay, so but we have 400 forms for the full instrument, for QUBIC full instrument. So the result of the interferometric pattern, when all the horns are open, is the synthesized beam. Yes, interferometric pattern is a synthesized beam. And this is the beam with which we observe the sky. If we do a cut and we look at the profile, we will see that we have main peak, primary peak, and secondary peaks. And these secondary peaks are separated from the primary peak by a distance that depends on frequency, on the frequency of the received radiation. Yeah. So the synthesized beam has multiple peaks, and the position depends on frequency. And this is very important for us, and I will tell you in a minute why. Now, this is the synthesized beam as measured in the lab. And this is, so on the left you have the measure, the data, and on the right you have the theory, and we have checked measuring with monochromatic calibration sources at different frequencies that the beam is behaving as it should, and that the peaks are frequency dependent, and they are nearer for higher frequencies. Yeah. So it's behaving as it should. Now, QUBIC, all the design that I have detailed in my previous slide refers to what we call the full instrument. However, now what we have in the lab is a smaller version with what that we call technological demonstrator that was assembled to test in the sky the capability to test if everything works as it should when we measure real signal in the sky and in the lab. Yeah, so this is a technological demonstrator. And as I said, many of the components are the same, but some of them are smaller versions. For example, to name some of the differences, the technological demonstrator has only one frequency channel, which are broad frequency channels, yeah, at 150, while the full instrument will have two frequency channels, at 150 and 220. Then another difference is that the horn array is smaller. In the technological demonstrator, we have 64 forms, while in the full instrument we will have 400. And the mirrors are smaller, and we have only then one focal plane, and it's smaller. It's 1/4 of the total focal plane. So we have 1/4 of the total amount of detectors, 248 TeS. So, what are the special features of QUBIC? QUBIC is a bolometric interferometer optimized to measure the primordial B-modes. And there are some characteristics that distinguish it from a traditional imager. So QUBIC, first of all, it scans the sky with the synthesized beam, which is the interferometric pattern produced by the Horn array that has multiple peaks that are each of them nearly Gaussian. It has a resolution of 23.5 arc minutes at the frequency of 150 gigahertz. The angular separation of the between two peaks depends on the frequency, and this allows us to reconstruct maps at different subfrequencies within the one frequency band. That is to say, within the 150 band, we can, thanks to this property of the beam, we can make maps at different subfrequencies, obtaining information at different frequencies from what in principle would be information from only one frequency in the middle of the band. Yeah? And lastly, the polarization grid is located before any optical component, except for the hardware plates and filters, and the sensors measure total power, so QUBIC is immune to cross-polarization, and this is very important to avoid the leakage between the E and B modes. So let's talk about the map making for QUBIC. Yes, as you can imagine, since the synthesized beam is non-trivial, the map making will be specific for QUBIC and non-trivial at all. The way we do it is through an interactive method, and we start with an initial map and a detailed model of the instrument. So with this initial map and the model of the instrument, we simulate a time-ordered data, a TOD. Then we compare with the real TOD, which is the signal measured by all the detectors at different times. And then we make a map and we iterate until we obtain conversions of the method, and the map will be the final map. As I mentioned 2 minutes ago, the separation between the peaks depending on frequency makes it possible to construct maps at different subfrequencies within the broad frequency band. Now, if we will compute maps from a multi-peaked beam and will reconstruct maps at different subfrequencies within a frequency band, it is expectable, and it happens, that the noise properties will be particular to this process. In what sense? In the sense that the noise will be spatially correlated because of the multi-peak of the beam, multi-peak beam, and the subfrequency maps will be also correlated in frequency. No? The different subfrequency maps will be correlated. And then, for example, in this plot, you see the correlation in different subfrequency maps for the for the intensity and the two Q and U polarization slope parameters. These correlation matrices were computed doing end-to-end simulations at 150 and reconstructed into 5 subbands. So this is the spectral imaging, what we call spectral imaging, because we are having maps at different subfrequencies. Now, about the spatial correlation that I mentioned in the noise map, spatial correlation of the noise map, what we find is that the noise is anticorrelated at an angular scale that is equal to the separation between the peaks. And this is produced because of the map making. Now, this is a correlation function. If we compute the angular power spectrum of the noise maps, we see that instead of being white noise, as it would be a flat line here, we have correlation at different scales. In particular, the scales we are interested in for the detection of the B-modes would be around 100, 150, or 200. And we see that the noise at these scales, at these angular scales, are smaller than the white noise, which is very convenient for the statistical analysis. So the main result here is that so the main question would be, what will be the performance of QUBIC to put bounds on the R parameter, on the tensor to scalar ratio? Well, considering these noise maps, and so that provides the sensitivity of QUBIC, you see here that this would be the case of white noise with the same level of noise as our maps, but in the case of this correlated noise map that we have, on these angular scales, we have a lower value of the error, right? And these lines are the predictions for different values, the BB power spectrum for different values of R. Yeah. So our prediction is that, assuming that QUBIC will observe during 3 years the full instrument, and assuming a good component separation method, that is to say that we can clean the CMB signal properly, we predict that we will be able to put bounds on R of the order of 0.015 at 68% confidence level. So that would be lower than the current bounds on R of the current experiment. So what is the current status of the instrument? Well, the technological demonstrator, which was assembled in Paris, was shipped to Argentina last year. It has some delays due to the pandemic, but it has arrived 1 year ago, and it has been transported to Salta, and it has been tested there in the lab in Salta. It's now being calibrated, and in the following months it will be, or by the end of the year, it will be shipped to the mountain, to the observing site, and it will start observing the sky and testing the spectral imaging capabilities of QUBIC on the sky. It will be able to characterize the foregrounds. We have a simulation that have shown that with the technological demonstrator, we will be able to characterize the foregrounds, the dust of the galaxy. Meanwhile, we will advance with the construction of the full instrument, the QUBIC full instrument. And as I showed, the infrastructure in San Antonio of Covers is very well advanced. To finish, I want to tell you that there has been a special issue of SHICAP journal with 8 special issues dedicated to QUBIC, with 8 papers on the performance of all the components of QUBIC and the overview of the science program and the spectral imaging capabilities of the technological demonstrator and of the final instrument. So you can check on the archives. They are all already published. They were published this April. and you can check all the details there. And more information you can see on the QUBIC website. So thank you very much for your attention, and happy to answer questions.
Many thanks for the seminar, and I will open for questions. So if anyone has questions to ask, you can raise your hand or ask. Wait, you open the mic? Okay.
Yeah, I would like to make a question.
Please go ahead.
Thanks. Thank you, Professor Claudia, for your presentation. Very clear. Yeah, you mentioned that there's an isotrope that is, produce the pattern, the B-mode is so you can put some constraint on inflation. As you said, this haven't been done yet. So my question is, if QUBIC is succeed and then can put this constraint, this means that inflation happened, or and then you can nail down what kind of inflation it is, how many degree of freedom, what kind of curvature, or what kind of perturbation, tensor perturbation are these? So what is the perspective for the inflation model?
Yes, I understand. So when our parameter is, this is very difficult, and QUBIC is not the only experiment trying to measure the B-modes. Of course, there are like 20 experiments trying to measure this signal, and it's very challenging. So I think that the first time that we will be able to measure the R parameter, the signal, will be just a limit on R, but we won't be able to see, I think, the detail of the spectrum as to compare with the details of given a particular inflation model. I can show you some plots. For example, these are the plants. No, I have them here. These are the plants constraints. That because with the temperature and E mode polarization and lensing and a lot of more data, you can put some constraint on the tensor to scalar and spectral index, but scalar spectral index in this plane, some constraints, and some models are already ruled out by this experiment, but a measurement of R will, I think, will be able to rule out some models, general behaviors of some models, but then the details of the spectrum, I think, eventually will give more information about which particular model is most likely to be true, let's say. Yes. So you see here where the result of plants 13, and now the constraint are more tight. So some models that were in principle allowed now are ruled out, but the measurement of R will help if there is. So you see, because here in this constraint the contours are cut, they are in zero, but if we eventually measure this, like a closed contour, we will be able to constrain even more this inflationary model. But there are a lot of models that predict the same values of R. So again, maybe we will have to go to the details of the of the power spectrum, which will be more difficult to measure because we will need more sensitivity to be able to study the details of the spectrum, as we do now. So here you can see this, the temperature and the polarization E-mode power spectrum now of Planck 2018, yes? But the first, if you go 20 years in the past and you look at this spectra, you would have seen like only regions of like where the value would be there, no? I mean, the errors were huge, and now they are like this. So the details of the cosmology is much more understood now. And I think eventually, in 20 years' time, it may happen the same with polarization.
Yeah. So we are at this baby step right now. We are. Yes, because the level of the signal is amazingly small. You see here in polarization, in temperature, you see microkelvin square. That is the level of the signal, and this it's very important to look at the at the plot, at the values, because here in polarization you are at the level of 10 to the minus 5 microkelvin, and I'm saying square, right? Square, sorry, because this power factor. But for polarization, for B-mode polarization, I'm saying it at least 1 order of magnitude less than that. It's nanokelvin, the signal. So the sensitivity is much higher than in this case. So it's important to have this in mind, to know that we are going in that direction. We will reach this sensitivity, but the technology still to be developed. I see. Thank you.
Thank you.
Okay, we have time for more questions. If someone wants to ask questions, actually, I have a couple of questions. I will take advantage of the Wenet's question, and I would like to I mean, I'm not an expert on CMB at all. When we talk the Cosmology, it is one that we can improve. We can constrain physics from inflation and also from late time cosmology and the cosmological parameters. And I would like to know, with the measurements of the B-modes, which kind of physics we will be able to improve more the constraints. This will be more important for inflation on these tensor to scalar ratio, or we can also improve the constraints of the cosmological parameters, or testing gravity and other stuff. And
it will be important for inflation, of course, but it will be, as I mentioned, it will be important to eventually, no? I mean, when it's measured, and you can see, as I said, when I said there are some caveats, there are some other signals that produce these B-modes. Well, if you can distinguish what are primordials and what are not, when that what in principle would be a contaminant, it contains a lot of cosmological information that you can have. For example, to study the magnetic fields, or to study the production of the secondary anisotropies, tensor anisotropies, as I mentioned before. And yes, of course, it's a cosmological parameter that would help to constrain the model better. So yes, this information will be included in the pack of cosmological information that we use to to test our model.
Actually, my second question, let me say in advance, sorry if it's a very silly question, but at some point in the seminar, you mentioned that there's something important that in QUBIC, that something that avoid some interferation process. I don't know. I don't remember exactly. In that sense, if I correctly understood, this means that it will be able to differentiate B-modes from primordial gravitational waves, and the other from the E-mode polarization. Is that correct? And it is important to differentiate these two B-modes.
I don't know if I follow the question. Do you mean? I don't understand. Sorry, I'm not sure if I understood.
Yeah, probably I could not put.
What do you say? Distinguish between E and B mode, or distinguish between different B modes?
Distinguish between this gravitational wave B mode and this lens B mode.
Yes.
Is that? I mean, is QUBIC will be QUBIC able to distinguish between them? And how important it is to distinguish them?
It's very important, but it's also very easy to distinguish because a lens B mode peak at a smaller angular scale, which in terms of the L multiple is a higher value of L. If the primordial power spectrum of B mode peaks around, let's say 1 degree more or less, is around 100 or 200, the L equal 200, let's say, the lens B mode peak around L equals 1000. So if you look at the spectra, you measure the spectra, even if you measure in large L beams, you will see that the signal, if the signal increase towards larger values of L, then this is lens B mode. But, and we are trying to measure a signal that peaks around lower values of L. But of course, as you see in this dashed line, there at these angular scales, we do have some lens B modes. And this has to be taken into account. But since we have already measured the B modes, the lens B modes, and we know the spectrum, we can remove the lens B mode from our analysis. In reality, when we try to put the constraints, we include the lens. We assume that the signal is lens, so some part of the signal will be lens. Yes, we separate them. Okay.
Okay, I see.
But the lens is already measured, has been already measured, and it's measured around this angular scale. And yes, and another thing I wanted to say about that is the fact that QUBIC has an angular resolution, angular resolution around 23.5, and so it cannot go to smaller angular scale as to measure the lens B modes. But we're not interested in that. Yes, there are other experiments that are focused on other science that have already measured the lens B modes, but maybe they are interested in the galaxies, so they are interested in having a smaller angular resolution to detect features at smaller angular scales. Yes, you understand?
Yeah, that's perfect.
So sorry, just a follow. Can I just follow up with this discussion just to see if I understood correctly? So the QUBIC is most sensitive where these two signals are easily differentiated, which is around this scale you mentioned. Is that right?
Yes, well, not more easily. The thing is that you will observe, you want to observe where the signal is high, is the highest, So QUBIC is prepared to observe in this angular scale, more sensitive, let's say, in this angular scale, where the B-mode, the primordial B-mode peaks. The question is there a contribution from length B-mode? Yes, there is, but it's not as high as where this length peak. And since other experiments have already measured this this lensing, we can consider that some of our radiation is coming from lensing and remove it. And I'm saying this in very simplistic way, but yes.
Yeah. I guess we are because in the past I guess this signal has already fooled us. I mean, the community. It was that this lensed B mode that was leaked from the E mode that people or something like that. No,
it was more the dust. The problem in the past was the dust.
Okay, dust.
Because as I said here, the dust is an emission that is very high, actually. So something I didn't say is that we will measure in the same region of the sky that BICEP has measured, because it's the cleanest region in the sky in terms of polarization, but it's not clean. It's not clean. There are no clean regions in the sky. Wherever you look, there is emission from the galaxy. We have learned that. So the dust is already quite well characterized, the dust emission in our galaxy, but it's there, and you have to take it into account. This is why you want to measure at different frequencies, because the dust, this is the RMS, brightest temperature at different frequencies. What this means is that if you measure at different frequencies the dust, and you measure in the temperature, let's say, the brightness temperature, the dust will be more bright as you go to higher frequencies. The CMB will have the same bright in all frequencies, because the CMB is a black body, so technically it has only one temperature, regardless of regardless of the frequency at which you measure, right? So you can separate, if you measure at different frequencies, you can separate what is CMB from what is dust. If you go to lower frequencies, then you will have the same problem with synchrotron emission. Yes, the dust go down, it's very low emission at very low frequencies, but then the synchrotron has a very high emission at low frequency. So what do? We go to the region in which this synchrotron and thermal produce the minimum amount of contamination. And that is around 150 gigahertz, 100 gigahertz. Yes?
Yes.
Okay.
Thank you for clarifying that.
No problem at all.
Okay, so more questions? I cannot see any raised hand. So let me thank Professor Claudia. Thank you very much for your seminar. It was super clear. And yeah, that's it. Thank you very much.
Thank you very much for the invitation. It was very nice. Hope to be there in person sometime. Anytime.
Yeah.
Okay.
Thank you. So goodbye.